So, good morning to everybody, and I hope everybody is fine. And in this video, I'll be talking about the transition of electron, and we have electron. It can be in the shells of a hydrogen atom, and as we understand from Bohr's theory that during the transition, once electron makes a transition, say from higher energy level to lower energy level, it emits radiation. It emits electromagnetic energy. So so this radiation emission, let us have some understanding of this radiation electromagnetic transition when electron has when it is inside the shell, it does not radiate. But when it has to make a transition, either by absorbing the external electromagnetic energy, or releasing the electromagnetic energy, when it comes back from higher energy state to lower energy state. So this is what's the point of intuition here, is that we want to understand this transition with quantum mechanical bases that can be intervened in understanding this kind of transition that we have in hydrogen atom. And uh, and to be precise, if we go back to what Bohr postulated was that there is the radiation, the electromagnetic radiation, and the frequency of this radiation is, say, for example, you have some higher state En minus some lower state En by H. Now, this is what gives us the frequency of the radiation when an electron makes a transition from some higher orbit to the lower orbit. And it's not very hard to show this kind of thing, that this relationship that we have here, it automatically comes in quantum mechanics. It automatically comes in evaluating the basic principles of quantum mechanics on hydrogen atom. And if we assume, for the sake of simplicity, if we assume that we have a system in which an electron is moving in some particular direction, and assuming that direction to be x. Now, if we do with that, and we can immediately think of writing the time dependent wave function, the time dependent wave function, and and this time dependent wave function, if I take it psi n for the energy state En, so I will have nu, the frequency of that state will come out to be En by H. And so, taking this thing into account, I can write down the wave function for this state as psi n it is psi n e to the power of minus times iota En by H times T. All right. So this let me use here. I think the right choice here will be to use. So this psi n is basically it is the time independent It's the time independent wave function. So this overall wave function that we have, that's psi n. And since I have to make it a little bit bold, but I should use some other tactics here. So let me use here phi n. Okay, so psi n is phi n e to the power of minus I e n by h times t. And this phi n is it's a time independent wave function. So phi n is time independent wave function. All right, so we can immediately think of the complex conjugate of this psi n. And what will be the complex conjugate? The complex conjugate. So that will be psi n star is phi n star e to the power of I e n by h times t. Because we understand when we take the complex conjugate of anything, all we have to do is to change the sign of the iota. So if I have an original function, if I have iota, I will replace it by minus iota, and vice versa. So what we have done is we have taken the complex conjugate of the wave function psi n, which is both the function of a wave function which is independent of time and multiplied by the time dependence. Now, if I have to write down the expectation value, which we have already discussed, expectation value of position. Okay, so what will be that expectation value? Will be it is minus infinity to infinity. Then we have then we will have x. Then we will have psi n star. Then we will have psi n. Okay, and dx. And we can immediately think of writing down the wave function that we have already written down. So what we are going to get out of this is minus infinity to infinity. X will remain there, and what we will have is phi n and phi n star. Okay, then we will have, we can see here when we multiply these two, for one I have negative and for another I have positive, so their product will simply give me 1. So what am I going to get here is this thing. So this will give me the expectation value of position of this electron. And we can see that this expectation value is it's constant. It's constant in time. There's no change in time, and by definition, we can say this expectation value is the function of position alone here, and electron at all is not oscillating. It's not vibrating, and electron is non-radiative in this case. So we can say here that the quantum mechanics predicts that a system in some specific quantum state. So there is a quantum state, some specific. It is basically wrong to draw the orbit, but for the sake of understanding, it's in some specific. When it is in some specific quantum state, it does not radiate. There's no radiation involved in it. And now, if we move on from here and we consider that that electron that shifts from one energy state to another energy state, and a system might be overall, if we think about it, it might be in its ground state, and if I say it like this, ground state, it might be in ground state, and 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 then it can have an excitation process of some kind, where you have an electron, and you will excite this electron to some another energy state. But when this electron was in this quantum state, we have understood that this electron should not radiate, because the expectation value of the position that we have found is independent of time. It's constant in time. So to say, or so to excite this electron, we can use some external agency. Say, for example, we will bombard it with some particles, like maybe electrons, or we may use some photons. So the point is that we have a particle in the ground state, and we will use some mechanism. We will use some mechanism to 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 act upon it, so that we can find that the system emits radiation corresponding to the transition from the excited state. So when we are in a position to move this electron to some higher energy state, we are able to see that there is emission of electromagnetic radiation, and and that corresponds to a transaction from this excited state to the ground state. Now, here I have a state defined as En. So this is the energy of the ground state, and I have a state Em. This is going to be the energy of the excited state. So that's the case. So what we find here is that that at some time during the intervening period, the system uh, existed in a state M, and we want to understand. We want to. We want to exploit the quantum mechanical rules, and to find the frequency of the radiation. Now, if I move on from here, and choose a wave function psi as as a combination of two states, say for example A psi n plus B psi n. Okay, so where we have this A, and A has its own complex conjugate, and the product of this A with its complex conjugate will give me the probability. It will give me the probability that electron is in state n. And at the same time, if I have B star, it will give me the probability that the electron is in state n. All right. So it must always be true, because some of all the probabilities for an overall wave function that we have, that should come out to be equal to one. And to take it in a very trivial sense, what are the possibilities that we can think of here is that this the probability of being in this state plus the probability of being in this state, it should always be equal to 1. That should be the case. Now, if I assume that, say for example, that this A is equal to 1, then B should be equal to 0. Only then I can have the overall value equal to 1. And when the electron is in excited state, for that A is equal to 0, then B should be equal to 1. To get the 1, that we have some of the two probabilities that's involved. And ultimately, I can again come back and say this A is equal to 1 and B is equal to 0. So while the electron is in either of the states, it's either in the state n, or it is in the state of n, there is no transition, and there is no radiation that we can talk about. And to have radiation, now if we think here numerically, to have radiation, it means A and B must have some finite non-vanishing values. So they must have a mixed values. Only then we can think of this state being between the state and between the state n. So both A and B has to have some finite value. Only then we can think of electromagnetic radiations. Only then we can think of the electromagnetic radiations that can be emitted during the process. So to say, so if I try to calculate the expectation value in terms of the wave function that I have written down here, so let me write down this the expectation value of position now in this case. So in this case, let's move on. So what we have is we want to find now the expectation value. So expectation value of what? Value of position. So that's going to be x. So what will be that? That will be minus infinity to infinity x times the wave function that we have written here. That's a star psi n star plus b star psi m star. So what is this? This is the complex conjugate of the wave function that we had written down earlier. So we have this wave function, because when we have to calculate the expectation value, it is minus infinity to infinity x psi star psi dx. So psi star, I have written down the psi star here, and then what should I get? Then I have to multiply this with a psi n plus b psi m, and this is dx. Now we can go with regular multiplication that we have here, and we can have x, okay, a star a. A star a will give us a square, because when we multiply a number with its complex conjugate, we get a number. So let me write it in a simple form. This is a square. Then what we'll have is psi n star. We will have psi n star, then psi n, plus b star, okay, star, then b star, then a, then we will have psi m star psi n. That should be the case, plus a star b psi n star and psi m. That should be the case, and plus b star, and b will simply give me b square. So this will be psi m star psi m. Close it and get some dx multiplied by it. Now here what we understand is that that the first term of this integral and the last term of this integral, they are not varying with time. They are in their own states, and we have understood that from the introduction of this topic. So these two states do not vary with time. So the second term and the third term that we have of this integral that we have here, these two terms, the second and the third integrals, they are only the two which can contribute to the changes, to the variations that are taking place when electron has a transition from one state to another state. And to do so, what we can do here is we can write down we can write down this these integrals in separate form, and out of them we will be choosing. I think it's better to write down this whole integral in separate form. So what we will have is a square minus infinity to infinity, then x psi n star psi n dx. This integral will not contribute to the variation. And then the another one I will have is plus minus infinity to infinity. Then what I have is b star a. Okay, then I have x, that's fine, and then I have psi m star and psi n. So here I'm going to write phi m star e to the power of plus uh, iota em by h cross t. Sorry, h, it's not cross, ht. Okay, and then we will have this psi n here. Psi n, again it's phi n. I chose it phi n, so phi n e to the power of minus iota en by h cross. It's not h cross, it's t. I'm habituated of saying h cross. So then the third term will have similar implications, we will have a star b psi n star and psi m. Okay, so in that case, what we will have is plus a star b. Let me write it outside, and then inside minus infinity to infinity, then x psi n star phi n star e to the power of iota en by h. It is what I had chosen it for. Okay, h then times t. All right, and then dx, and then we will have the integral in the form of this term. And as I said, that the first and the third integrals, they do not contribute. So what we are interested here in, they don't contribute to the variations, they don't contribute to the changes that can occur when the things are happening between the shell n to n. Now these two parts that we have, if we have to get some information from these two parts, what should we do is we can think of writing these integrals in terms of say, if we have, say, e to the power of iota x, iota theta, this is cos theta plus iota sine theta, and we have e to the power of iota and e to the power of minus iota there, and for minus iota here I will have minus iota sine theta. So when we will substitute them, and what we will have from those two terms, because only these middle two terms do have some implications to our problem. So what will I get is cos of em minus en by h. I it was omega, it's times t minus infinity to minus infinity to plus infinity. Then we have some x, and then we will have b star, then a times we will have psi m star, and we will have phi m star, and we will have phi n. Okay, then we will have after that there will be some plus involved, and then we will have a star b, then we will have phi n star and phi m. This will be the case, and then we will have some plus iota sine of this em minus en by h times t, and then the same thing will be repeated here in terms of the integral. Okay, now what we are interested is to talk about the real part of this whole thing, this whole shit that we have obtained, and if I take the real part of this thing, that will be this cos of em minus En by h times t. And I can think of uh, I can think of writing this as cos of uh, cos of Em minus En by h by h. This can be thought of as cos of uh, cos of nu t. Okay, so that this nu that we have, this nu that we have, because we have chosen h in every case. If we had chosen for instead of h, if we had chosen h cross, then we would had come up here with 2 pi nu. But since we have only chosen h, so here I can write cos of nu t. So this nu that I will have, this nu I will have be equal to Em minus En by by Em minus En by h. So this is what we can obtain by taking into account the real part of the two terms that we saw in that integral, in the middle of that integral. And what we see here is that the electron's position is oscillating. Electron's position, because we are calculating we were in the domain of expectation value. So electron's position is oscillating. It is oscillating sinusoidally at some frequency nu equal to Em minus En by h. So the point of intuition here is that when the electron is in the state n or in the state m, the expectation value of the electron's position was constant. We have seen that at the start of this presentation. But when the electron is undergoing a transition, when it's undergoing a transition between these states that we have defined, its position oscillates. Its position shows oscillation. That's not purely geometrical in nature. I can't have any geometry to demonstrate that. But for the sake of understanding, I'm trying to use some geometrical considerations here. So what's going on is that the position of this electron is oscillating, and it is oscillating with the frequency nu, so that the electron certainly is like it's like an electric dipole that radiates electromagnetic waves of the same frequency, and this result is the same as that was postulated by Niels Bohr, and it was experimentally confirmed. And what we see here is that quantum mechanics gives us this equation. It gives us this equation without the need of some special assumptions. We are automatically reaching out to a relation where we find an oscillating position of an electron by using wave mechanics. So that should be the case.